Hey, how's it going, everyone? I hope you're all doing well. Welcome back to day 5 of the 30-day Leak Code Challenge. Now, today's question is called Add and Search Word Data Structure Design. Before I cover the question, let me just acknowledge the fact that I know there are some X's over here and I haven't been posting a video every day, but I may have underestimated how long it takes me to sometimes complete these questions and how long it takes me to actually edit the videos. So I apologize for the fact that they're not out every single day, but I am trying my best. Like I mentioned in my previous videos, I'm not a complete master at algorithms and data structures yet. I'm also just figuring things out and learning as I go, and hopefully you guys can learn along with me. So regardless, let's get into the video. So the description says we need to design a data structure that supports the following two operations: add a word and search a word. So from the requirements, it seems pretty straightforward, but if we keep reading, it says search word can search a literal word or a regular expression string containing only letters A to Z or a dot. This dot means it can represent any one letter. I'm going to call it a wildcard character. Let's take a quick look at the example here. So first we add a word called bad, then we add a word dad, then we add word mad. Then we search for pad, which is false because we never added pad. We search for bad, which returns true. We search for dot ad, which means any character followed by an ad, which in our case is true because we have bad and dad. And also we search for b and then any two characters after it. So initially when I read this question, some few thoughts that came to my mind were, well, why can't we just use a string? Why do we have to make a new data structure? Why don't we just take the word that we're trying to add and append it to our string? And when we're searching, let's just check if the word is present in our string. That's a pretty naive approach to it because one, you would have to search through every element of the string and see if the word that you're searching for exists in it. Also, it would make it more complex to handle situations where you have a wildcard character. I thought about the same thing with an array, but it's the same idea with that, right? You don't want to have to iterate through every single element of the list or the string to find a word that you're looking for. So we need a way to efficiently store strings and have a fast lookup time for searching a word and for adding a word. So I want to introduce a data structure that I completely forgot about, to be honest. And I actually had to refer back to my algorithms textbook from last year. So I was going to use a PowerPoint to show you guys what a trie is and how to work with one, but it was getting really annoying to work in here because I don't have a stylus. So I'm just going to go old school and show you on paper. So let's talk about some basic points about a trie. A trie is basically a tree structure, and that means there's going to be nodes and edges. The nodes are going to store characters in our trie, as you can see here. Each node contains a character. All right. Each node also has our children, one for each character in the alphabet. So essentially, that means each node in here is going to have 26 possible children. Obviously, we're not going to display all 26 because there's not enough space. Each node also knows if this is the end of the word, and we'll represent that with a star for now. In our code, we will likely use a Boolean. So let's look at our trie over here. We start with the root node, which basically represents the empty string. Everything starts from the root node, right? Every string you create starts from the empty string. So we have the words bad, dad, buy, and bake, right? If we want to represent bad, for example, we start at our root node, we go down to the node B, which leads to the node A, which goes to the node D. Now notice here that every word that begins with a B starts at this node over here. So the word buy is also found starting from this letter. This is the node that starts every word with BA. So we have BAD, we have BAKE, which is bake, and on the left over here, we have a node that starts with a D, and that goes to dad, for example. If we wanted another word that started with a D, like done, for example, we would go to our node that has D, we would add an O, we would add an N, and then we would add an E. Great. So now that we've talked about what exactly a trie is and how it looks, let's talk about how to perform a search operation. Okay, let's say the target word that we're looking for is bake, for example. All right. So we're going to start off by by iterating through each character of our target. Let's say we start with index I equals 0. All right, the first thing that we're going to do is start at our root node. Okay. So we'll start at the root and we'll set the root as our current node. All right. So current is over here. Okay. What we'll do is look for a child of the current node that contains target at index I. So again, we'll start at the root node, mark that as current, and then look for a child that has target at I. So in our case, we're going to start at the root and look for a child that has the letter B. So we'll traverse to this node and mark this as our current node. So now we're at B. We'll look at the next character of our target. Again, let's look for a child of our current node that contains the letter A. So in this case, we find this node and we will traverse here. Now this is our current node. Let's look at the letter K. Let's find a child of A that has the letter K. In this case, we'll traverse to this node. Okay? Now from here, let's find a child of K that contains the letter E. So we'll finally traverse to this node. Now at the end, one of three things can happen. One, we reach the end of the target word, in our case E, and the current node contains a star, which means it's the end of the word. So that means we have a search hit. So the second outcome that can happen is we reach the end of the target, which is E, and the current node we're at does not have a star. That means we have a search miss because we haven't reached the end of a word after traversing the entire target. Option number 3 is simply that the node is not found for the target at I. So for example, if this E didn't exist and we were looking for bake, then we would have a search miss because K does not have a child that's an E. So in 2 cases, we have a search miss. In 1 case, we have a search hit. So the last thing that we need to take into account for the search is the wildcard character. What if we hit dot in one of our searches? So for example, if we had the target B.D, here's what we'll do. We'll start our search normally. So we'll start at the root node. We'll look for a child that has the first character of the target, which is B, and we'll traverse to that node. Now this is our current node. Now, when we hit the dot character, what we need to do is recursively call search on every child of the current node with the rest of the target string. So the reason for that is because our trie doesn't know which child of B will lead to a search hit, because the dot character can mean any character, right? So what we'll do is recursively call search on every child of B and see if any of those calls return true. So for example, if we choose to traverse down this path, we'll have a Y, but Y clearly does not have a child that has a D. So this is going to be a search miss. So we'll go back, then search will be called on the next child of B, which is A. And from A, we'll look for a child that has the letter D. So we'll traverse to this node. And now that we've hit the end of the string and our current node has a star, we can return true. Recursively call the search function with the rest of the string after the dot character on every child of the current node. So like I said earlier, if our current node is B and we hit a dot, we'll go through all the children of B and see if any of those recursive calls returns true. If any of them do, then we have a search hit. Otherwise, we have a search miss. But once we get to the code, it should be more clear. Let's also talk about adding to our trie. The way we'll approach this is first, we'll start off by performing a regular search. Let's say we're trying to add the word doc. Okay, so like I said, let's start by performing a search. So we'll start at the root, like it says over here, and we'll look for a child that has the current character of our target. So we'll look for D. We'll traverse here and mark this as our current node. From here, we'll look for the next character, O. In that case, we'll traverse to this node. Now, as we're traversing, one of 2 things can happen. So one, the node that we're looking for is not found. So in our case, when we reach C in our search, we can see that O, which is our current node, does not have a child that's a C. So in this case, we'll add a new node with the missing character and we'll repeat that process. So from O, we'll add a character that's a C. And now we're at letter K. Since we just added this node, obviously it doesn't have any children, So we'll add the letter K as a child of this, and we'll put a star beside it to mark the end of the word. So I just made a note here. We'll end it with a star. But the second option is that we find the node for the last character of our target, but it's missing a star. So for example, if we already had DOCK in our list, in our trie, but there was another character after the K, for example, like S, and this did not have a star over here previously, what we'll do is we'll add the star because we reached the last character of our target, and the only thing that's missing from our trie is the star character to mark that this node is actually the end of a word. So in both cases, we'll have successfully added the word because in case number 1, we add new nodes and mark the last node with a star representing end of word. In the second case, if we already have the node there, we'll just put a star or end of word boolean to mark that this is the end of the word. So if this sounds a little bit too abstract, let's just get to the code and see what it looks like from there. Let's start with the init function. So for some parts of this code, it might get a little bit long. So what I'll do is I'll write the code, I'll speed it up for you guys, and then I'll quickly explain it after I'm done typing it. So this init function is basically going to initialize our root node. Okay, so we're going to first start off by setting self.children to an array of 26 none characters. And we're also going to set self.isEnd of word equal to false. Because remember, every node has a boolean of whether this node is the end of the word or not. So obviously the root node, we're going to start off with false. All right, so let's go to the add word method. So our current node is equal to self, which is basically going to start us off at the root node. Okay, so first of all, what's going on here? What we're saying is we'll go through every character in our word, all right, as I showed you in the example on paper. So in plain English, what it's saying here is if our current node doesn't have a child that contains the character that we're currently at in our word, then we'll create a new word dictionary at this location of the current node's children. So let me quickly explain this or char thing. We want to specify an index number of the current character that we're looking at. So the way we'll do that is calculate the Unicode for our character and subtract the Unicode number for the letter A. And that's going to give us a number between 0 and 25, which will mean that we get a unique index position for every character in the alphabet. All right, so one of the things that I did was move this subtraction calculation into a variable called char index. And I just used char index instead of that subtraction because it's easier to see here. So after we're done creating our new node, if we don't have a child that has the character we're looking for, we're going to traverse to that node. So we're going to set current node equal to current node.children at char index. And this effectively moves our current node to the new node that we just created. Or if it already existed, we'll just traverse to that node. And so after that, the loop is going to repeat for the next character in the word. Again, it's going to look for if that current node has a child that contains the character index that we're looking for. If it doesn't, then we'll create a new node for that character. And then afterwards, we will traverse to that node. So essentially, with every iteration of this loop, we're moving to a new node. And then after this loop is done, we're going to mark our current node as the end of the word. Because at this point, we would have gone through every character in the word that we're trying to add, and we either created a new node for it, or we traversed past it if it already existed in our trie. So this is all we need for adding a word. All right, now let's talk about our search method. So we're going to start off in a very similar way to the add word. All right, we're going to set current node to self to start at the root node. And then we're going to start going through every character of the word. So first, we'll just set the character to word at I. Now let's cover the wildcard case. So what's happening here is if the character that we're looking at in our current word is the wildcard character, then what we want to do is loop through all the children of our current node because we don't know which child of our current node is going to be a search hit. So we're going to loop through all of them. So while we're looping through, if the child we're currently at is not none, then we're going to perform the search function. Again, this is recursive. We're going to perform the search function with all the characters that are after the wildcard character. That's why we're doing I plus 1 colon. This is basically slicing our word from the index after I all the way up to the end of the word. If any of these recursive calls to search return true, then when the call stack comes back, we're going to return true. Okay. If we've gone through all of the children of our current node and none of the children return true for our search, then we're going to return false because we've tried every child of the current node. So let's cover the case where we don't have a wildcard character. This is the easy part. All right, so let's say we didn't hit a wildcard character. We're looking for a regular character now. So first, like we did in the add word method, we're going to calculate the index that our character must be sitting at in the array of children. So we're going to calculate that and store it in char index. All right. So if our current node's children at that character's index is none, in other words, we don't have a node for where this character is supposed to be, then we're going to return false. Because now we're at a character in our current word that does not exist in the children of our current node. Otherwise, if this never happens, then we'll just set our current node to currentNode.children at char index, which basically just means set our current node to the child that contains the character we're looking for. All right, so finally, if we've gone through this entire loop and the current node is not none and the current node that we're at is marked as end of word, then we're going to return true. And that marks the end of our search. That was longer than my normal videos, but there was a lot of groundwork to cover before we can get to any of the coding stuff here. So if you guys learned anything new in terms of the theory and concepts behind implementing a trie, or if you tried implementing a trie, then leave a like and a comment and feel free to subscribe. Thank you guys so much for watching if you're all the way here to the end, and I'll see you in the next one. Thanks.